Okay, thank you, and good morning, everyone. I'm David Barker with Quintel Technology, and again, I wish to thank Telefonica for the opportunity to present a topic on base station antenna evolution and revolution, and hopefully this builds on some of the discussions yesterday morning and this morning. So I've also got a graph on the gap between data demand and the expectations. So this is from Verizon, a public domain document, showing you, as we've seen this morning, how we solve this. So the capacity crunch, we're all aware of this. It could be 50 times, it could be 500 times. We don't really know, but it's going to be a large number. Okay? How is it solved? We've been talking about this the last 2 days. More spectrum. Given what Ofcom, FCC, the Indian regulatory authorities, they're all promising about 500 megahertz over the next 10 years. That's about another threefold increase on where we are today. There's also some creepage in the spectral efficiency. Not a great deal, as communicated in the earlier presentations. We're reaching Shannon's limit, but through some clever additional higher order MIMO techniques and beamforming, we can argue another 3 times increase. Okay? That's not going to get our 50 or 500 figure. So we're all in agreement that some higher density, higher reuse topologies will give that benefit. I think that's a concluded statement. So small cells are the answer. However, traffic's very lumpy. And going back to the keynote yesterday, coverage is a key point. I was at a conference last week where it said about 20% of the cells in the network would need to go cell splitting into small cells. The 80% are still about coverage, and they will get challenged for capacity. So they may not need the 500 times increase, but they need some good increases going forward. So when we say 500, not all cells will go by 500. Okay? It's very lumpy, that demand and projection. So if you like, dense urban may go 500, perhaps rural would be, or suburban, a different figure. So this talk is about the macro layer and how we might see some improvements in the spectral efficiency in that layer. And again, I just reiterate the Shannon's limit. We've more or less reached this, but of course, MIMO effectively adds parallel channels where we can add additional capacity. So I'll just give a quick picture of spectrum evolution. I'll give a European picture here. Back in the 90s, we had GSM 900, and then later on in the 1990s, we had 1800, and that was all standardized against GSM. And then we had UMTS 2100 for the big bucks. And then, of course, recently in Spain, Italy, Germany, Sweden, and I believe France of yesterday issued the 800 and 2600 spectrum. So that's destined for LTE. Up until then, we had receive diversity-only antennas. So the uplink got the benefit to allow the handset to reduce its power. But we're also now having transmit diversity and spatial multiplexing to increase the data. We also see some refarming there in the 1800 band, of course, which some operators are doing, and at the 900 band for UMTS. Then perhaps in a few years' time, we might see additional digital dividend spectrum. That's been talked about now in regulatory environments. We might see more refarming. We might see release 10 coming along, so techniques like coordinated multipoint and beamforming. And then by the end of the decade, we might have additional bands. We've got 1.5 there, 2.3. I've shown the TD band for 2600, and perhaps white space can get exploited. We saw that yesterday. TV broadcasters maybe move further down or interleaved into that. So a lot of bands coming along. And again, I just reiterate, people like the FCC have promised or indicated 500 megahertz would be available with a hands-off approach to speed up the allocation cycle. Incentive auctions we talked about, trading a spectrum. And of course, LTE Advanced is aligned with band bonding. I use parts of this spectrum or different bands to make an aggregate channel to deliver my 1 gigabits per second peak rate for LTE Advanced. But of course, as I introduce more spectrum, more bands, I have additional inter-system interference and intra-system interference. And these are things which won't go away and are actually practical issues which we all need to address. We're seeing this with TV, public safety, GPS, light squared is an example in the US for inter-system interference. And of course, just building on Ronaldo's presentation, on the presentation yesterday, we could move to cognitive techniques. So dynamic spectrum access, building on the white space model as we go forward. There's an example of channel 51 in the US where effectively low block 700 can't be used. It's an example of would-be interference or some spectrum sterilization. Just a bit about antenna evolution. I've titled this Maxwell's Laws, not Moore's Laws, or Cooper's Law. Maxwell didn't promise any great increases in antennas in the same physical size, at least. Back in the 80s, we had omnidirectional, then sectored, then we went di-cross-polar. That reduced two antennas into one antenna in the same physical space. Then we had variable tilt, because we went to one-by-one reuse schemes for WCDMA. Interference, softer handover needed to be important parameters. Went multi-band. And we're at a point now where more bands are coming, 800, 2600 for Europe, and need for more spectral efficiency. So active, adaptive, MIMO, how do we solve this? On one hand, there are an emergence of multi-port antennas coming out in the market. So there are some clever topology techniques which have emerged, and we've played in that space, where I can add more and more ports to the antenna. At the same time, almost separately, there's adaptive arrays, which the Chinese have pushed forward with their TDS-CDMA technology, reconfigurable arrays, and of course the MIMO technology. And in many ways, they are somewhat separate at the moment. Multi-band and fully adaptive are somewhat mutually exclusive. So on one hand, we've got space efficiency, space on the mast. On the other hand, we've got spectral efficiency, increasing my bits per second per hertz. Again, just a quick word on how spectral efficiency is creeping up in the, as we go forward. And again, just building on what we heard previously, we're not promising any tenfold increase here. It's very, very slowly creeping. So release 8 of the standards, 2x2 spatial multiplexing MIMO. We'll see release 9 introduce a technique called dual layer beamforming and multi-user MIMO. So instead of increasing the data rate to a single user, I increase the capacity of the cell. And then as I go through the standards, I'm going to bring in multi-cell MIMO. So 2 transmissions, 2 base stations down at the cell edge. I can duplicate that information and get independent spatial channels. I can add higher order beamforming to collapse my C to I on top of that. And then, of course, I could go to multi-cell, multi-user, and beamforming. Okay? I've just drawn some illustrations of the base station antennas that might deliver that. And there were some recent 3GPP study items which characterize some of these spectral efficiencies. And they're all about increasing the cell edge input performance. There's a very wide discrepancy between the average and the cell edge experience. A lot of these techniques address the cell edge. I've got some figures there, which is really some averages of the bits per second per hertz for those various techniques. As I say, we're not promising 10 times. It's something of the order of 2, 3, 4, perhaps 5 times increase. But nonetheless, things which can be exploited, particularly in the macro network. I'm going to come back to this slide. I've left it in for, it just talks about dual layer beamforming. Let me move on in the interest of time. Just to introduce Quintel and where we play, we have 2 product families. On the left is what we call multi-serve. That's multi-port antennas. So when I've got 4, 5, 6 bands, that's what we're trying to do in one antenna. Primarily aimed at single antenna per sector sites, but also has applications on 2 and 3 antenna per sector sites. And I can give an example in a moment. So it's about packaging it in the minimum form factor. On the right-hand side, it's taking the same technology, but rather than doing multi-bands and multi-technology, it's about doing adaptive elevation beamforming. Now, this is the thing which we're particularly excited about. It's delivering some of the spectral efficiency features, but indeed on a passive platform. So we're approaching it from a different direction. And again, I'll build on some of the industry movements in that adaptive beamforming space. So it's what we used to call the smart antenna, the adaptive antenna. They've been around for many years, but only becoming reality now for cellular deployments, both from a size and cost perspective. Just a quick word on how our technology works. It's a very simple technique. I show a standard remote electrical tilt antenna here. Panel antenna, you see many millions of them around the world. I have a power dividing network which divides up the RF signal, and that goes into mechanical phase shifters, which then drive pairs of elements. What I'm trying to do is create a phase front across the array, which then gives me beam tilt. That allows me to control the footprint, but more importantly, the interference between cells in its cellular topology. The way we do that is we have a vector network combining microwave circuit here. We have a single phase shift. The amount of phase shift there gives beam tilt. What that allows you to do, for example, I could have two different bands. I could phase shift them independently and combine them at the antenna. Independent tilt for two bands. Okay, but that's not what I'm talking about today. That's what we're doing. That's what we've been doing for the last few years. So just a quick example of the types of antennas we're introducing into the US or America's market here. 4 bands of one array, of one antenna. It's 2 physical arrays, but in one package. And likewise for Europe, we're considering something along the lines of a 10-port antenna to deliver 4-branch 2600, legacy 900, 1800, and the 800 band. So there's space efficiency techniques based on our current application of the technology. Just a quick example of something I mentioned earlier, the intra-system interference. I use a US band plan here, and it's creeping up more and more. What I show here is 2 blocks of 700 spectrum. I do a PIM analysis, passive intermodulation. I don't get any third-order products, so I'm good. My receive band's quite clean. I don't have to worry about it. But if I acquire more spectrum, let's say I acquire some A block, 700, I now have some PIM products, if I use all 3 bands contiguously, which would fall into the receive. I didn't have this with GSM, because I wouldn't use all the spectrum all the time, of course, or I could frequency hop around these. I have 5th order and 7th order as well to consider. And as I go up in power, these problems of passive intermodulation become a real problem. And we're seeing this with networks across the world. One solution which we've pushed is, it's actually going, rather than the future, we call it a back to the future solution. You put all the transmission onto one antenna, and you allow that to create PIM, but the receive is actually completely decoupled. We have a receive antenna. What this allows you to do is add bands which would otherwise cause passive intermodulation problems. So it goes back, you may remember 20 years ago we had transmit and receive diversity, of course. So it's a back to the future. So I want to go backwards rather than forwards on this one. Another back to the future solution, particularly in Europe, we all had space diversity antennas. In the late 90s, we moved to cross-polar. It was an example of reducing the antenna count. But we forget actually that space diversity actually gave us a little bit of a benefit, particularly in rural, suburban type radio channels. Again, if you've got 2 antennas per sector, you can, for example, put LTE 700 and AWS here, again, an American example, across 2 poles. In fact, it's hybrid polar space diversity, which actually gives me slightly better than just V-pole diversity. This is an Ericsson paper showing on the downlink now, transmission diversity or spatial multiplexing, I have a dB of spectral efficiency gain. And there was a paper a number of years ago, indeed by Telefonica, which I've got here, which actually characterized that I got a dB improvement on the uplink. So sometimes we forget why we move to cross-polar, and if we do have 2 antennas with a sufficient spacing, perhaps that's a dB we can get straight away, a dB spectral efficiency we shouldn't ignore. Okay, so let me say what is an active antenna. Okay, I think Jaime raised a question on active antennas yesterday, but I'll just go into a bit more detail on how we play there. This is all about the spectral efficiency. So, on one hand, it's about creating a single unit on the top of the tower. Okay, rather than a base station or a feeder or a remote radio head, I have a single box. So I have my antenna. Is that my phone? Sorry. Yeah, there you go. Sorry. So you could integrate a remote radio head and close couple it to an antenna array, a normal antenna array, perhaps as phase shifters. And that's one idea of an active antenna. The classic view is actually a single power amplifier behind every element. And what I show here is something in the order of 16 amplifiers driving 8 cross-pole antenna elements. You can also get variations where I'm driving groups of arrays. We're essentially offering a different topology which will deliver smart features. These two on the right can deliver some smart features. I can do adaptive elevation beamforming. I can do tilt by technology, tilt by scrambling code, tilt by operator for RAN sharing purposes. So once I've got access to forming the beam, I can do all sorts of smart or adaptive thinking. This one, it can't. Remember, I'm putting all the RF energy into an RF distribution network. It's fixed in terms of what it goes out of those antenna elements. I can adapt it here, I can adapt it there. What we're proposing, and as you might remember how our technology works, we're relying on differential input. So if I got 4 amplifiers, I could drive 2 into each corporate feed, and I could drive these differentially, so I create a tilt. In fact, if I get into the baseband, I can start playing with different OFDM subtones or different RF carriers in the same bandwidth. I can start tilting for different carriers, different information, etc., etc. But the advantage is I can have that as a remote radio head. That is, in fact, and I've highlighted, this is standard, what's called a 4T4 base station or remote radio head. It's standard ecosystem hardware. That could be close-coupled remote radio head. We're all familiar and comfortable, or becoming comfortable with that type of deployment. If you're uncomfortable with that type of deployment, in other words, electronics at the top of the mast, you could have a bottom-mounted remote radio unit, or indeed base station, with RF feeders going to the top. This could be a 200-foot, 60-meter tower, where it's difficult to access if there's any failures. So what it's saying here, we can have smart adaptive features, which I'll come on to and expand in a moment, but without necessarily having electronics. You can close package the electronics, and remember, I'm reusing topologically the same hardware. And that hardware will exist in the ecosystem from various OEMs. So once I've got this architecture, this active antenna architecture, where I can deliver differential signals, I can start tilting in many dimensions. The one really of interest to many people is this elevation beamforming. It's an emerging field of study by a number of organizations as a spectral efficiency technique. The idea being, I'm taking energy, rather than talking to everyone on, let's say, a 2-degree tilted beam, which all the energy goes into my next cell, what I'm doing is if I've got some radial distribution of users, I can send energy where it's needed and not where it's not needed, in other words, into the next cell. And technologies like LTE are very susceptible to intercell interference and have very little intracell interference. So therefore, this type of technique may hold some, or has some promising results. Again, I just show some examples here of what you can do once you're in that digital processing domain. One thing which we're taking to trials and very excited about is actually not relying on what's a Release 9 base station. It's actually taking a standard LTE Release 8 base station with 2 transmits and 4 receive channels. So 2T4 is the nomenclature here. And what we do is we give the downlink a static tilt, but we let the uplink come directly into the base station. Remember, the technology we have is differential phasing. Those receive lines go into a maximum ratio combiner or interference rejection combining circuitry, and effectively, we let the MRC circuit apply the phase shifts. What it's doing is, on a per-user level, each user gets his own uplink beam to maximize his C2I, okay? So I'm using standard, common, mature MRC circuitry to be my adaptive algorithm. So nothing bespoke, uses off-the-shelf type of approaches. But this, again, completely passive. So I've got flexibility of integrating the electronics into there, having it close coupled or at the bottom. But again, it's using standard technology. Could work with GSM as well, and to a lesser extent with UMTS. UMTS has a lot of intra-cell interference, so spatial filtering and elevation is not necessarily as effective as it would be for LTE or GSM. And then, just building on that, and where we see the future, at least from our perspective, is once I'm into release 9 of the standards, and perhaps release 10 before all the feature sets have settled, is I'm not just doing elevation beamforming on the uplink, I'm also doing it on the downlink. And that's where I'm getting the downlink spectral efficiency as well as the uplink spectral efficiency. So, in fact, what we're doing, we're not really beamforming, we're doing tilting. But that's all you might want to do in the elevation plane, because I have a very narrow field of view this way. Okay? I'm not tracking multiple targets as in a radar system. I only want to direct energy down towards the user and a null towards the next site. I have one trajectory or bearing where the interference is. So collapsing the beamforming problem to a single vector per polarization, we would deem as an elegant sort of solution to the spectral efficiency problem. And again, I've just drawn a couple of geometry pictures here. The technique is suited for macrocellular, where I've got low angles of dispersion in the elevation plane. In other words, energy is dispersed by scattering, let's say from the user. His multipath comes in at a relatively narrow range of angles. In other words, I want to point a beam to him. A single beam, that's typically 6-7 degrees in the elevation plane for beam width. A guy closer in, slightly fatter beam, his dispersion is slightly wider, but nonetheless a different angle. Some simulations there which we're getting involved in. The idea is about increasing the cell edge throughput and fairness with various scheduling schemes. And I remember that can be a 2T4R for the uplink only. What I would say is, and this goes to small cells and different environments, the fully adaptive active antenna, it's capable of putting phase and amplitude control per physical resource block in LTE at each element. In other words, I can actually create any arbitrary beam. I've just argued at macro sites we don't necessarily need that. However, if I'm in a metrocell, picocell type environment, or relatively just a very dense urban environment where I'm scattering off rooftops, you tend to find my scattering volume may encompass the base station antenna, and my elevation multipath can be quite varied. Having a tilt is no good there. It didn't do anything for you. Actually, I want to fully beamform. I want to arbitrarily beamform. And what I've shown here is an idea of I'm mopping up the different multipath and elevation. So I actually need full control of all the active antenna elements. So what we say is this is fantastic and definitely needed for picocellular environments. And perhaps these active arrays tend to be, let's say, not multi-banded, but I might not need all bands in the microcellular environment. When we use a quintel topology, remember that's a passive array. That could be a 10-port antenna, which is a mature or maturing technology, where one of the arrays is the adaptive part, the LTE part. So we can support the legacy on top of the adaptive. And I'll just show a quick example. What I've got here is LT800, 44 going into a passive antenna doing its adaptive beamforming. But I hang off it a legacy GSM 900. Perhaps that's some equipment I'm not refreshing, but I can go in there and set a static tilt and hang it off the same array. Again, completely passive, legacy 900. The LT800 can have adaptive smart features. So we say this is spectral efficient as well as space efficient in terms of it's one antenna, and in many ways operationally efficient in the sense it can have the option of having electronics at the bottom, not necessarily at the top. And again, I'll just go through the build. Yeah. And this is my last slide, which is I guess, Jaime, you raised this question yesterday. I think there's a lot of excitement in the spectral efficiency techniques, beamforming and adaptive tilting, for example, can provide. But at the moment, the industry is inherently single band, perhaps two bands using active antennas. So I do a world of the conventional world where, let's say I've got 4 bands. I may have 5, but this might be macro, so 2600 may not be a main feature. If we didn't exist, or active antennas didn't exist, then perhaps 2 dual band antennas with a couple of remote radio heads for the high band services might be seen there. Currently, we're seeing in the active antenna world, let's say I've got a passive 900. My GSM is my cash cow. I don't want to disturb that. I leave that as it is. But I may have 3 or even 4 active antennas, which are typically driven by fiber, but inherently single band. What we're saying here is that can be completely passive in terms of the antenna, deliver all the legacy bands, and deliver smart adaptive elevation beamforming type features. It requires, or we require, some interaction with the OEMs, but it's a fairly simple interaction in terms of the protocols. But the idea being as well, this can present a lot of weight, particularly if they are ultimately multi-banded. But with remote radio heads, it gives you some flexibility of weight distribution on certain sites. So I've drawn a couple of US sites here where you can't go beyond 30 kilograms on those arms, otherwise it'd require some strengthening. But with a remote radio head with short feeders, moving to a passive antenna allows me to distribute that weight from zoning as well as wind loading and criticality. So that's the end of my talk. So thanks for your attention, and I guess we'll take questions as part of the panel or now. Okay, so I take questions now? Okay, so yeah, thank you for your attention, and are there any questions for now?